Hello,
Okay.
everyone, and I'm really happy to be given the opportunity to present remotely some results of mine, some very recent results. What you see on the background of the slide is a rendering of a black hole and its accretion disk. The closer you get to the black hole, the hotter the accretion disk, and you can see that as a color gradient. Also, the relativistic effects will be greatly enhanced the closer you get to the black hole. So, my name is Eugenio Bottaccini, and today I'll be talking about modeling the black hole spin, why this is so important for the acceleration of cosmic rays, and why this is still an open issue. One of the most suitable astrophysical environment for different type of accelerations of particles, that's the extragalactic jets. For example, this is one and the same source observed at different frequencies. On top you see the X-rays, to the left the radio image, to the right the image from the Hubble Space Telescope. And these images are all to scale, and you clearly see that the jet originates in the center of the galaxy itself. So now when we have a jet pointing at Earth, like the jet of 3C279, then you have a unique opportunity to model also the content of the jet. So you might remember this one. This was actually the largest flare ever recorded from 3C279 at high energies, and it dates back to 2015. So for this flare, we managed to observe the source with the Fermi telescope. These are the Fermi data, the integral data, the Swift XRT data, and here we have near infrared all the way to UV data. So we modeled this SED with a leptonic model, and here come the single component. You have the synchrotron component, the external inverse Compton on the broadline region. This is very well known from independent observations in the past as well. Then we have the inverse Compton of the photons arising from the accretion disk entering the jet, and eventually also the synchrotron self-Compton component. However, you can model this SED, also the spectral energy distribution, also with the leptonic model, the green line. And if you keep your eyes peeled for the single components, then you see you have the electron synchrotron component and also the proton synchrotron component right here. It goes up. So now we know that cosmic rays are accelerated in jets and that the composition can also be hadronic. This is a fundamental piece of information if you want to get neutrinos into place. So the question is, do we really understand how and why these jets are formed? Um, we know from general relativistic magnetohydrodynamic simulations that accreting and rotating black holes, they can actually form jets. The higher the spin, the higher the jet power. It is generally believed that a supermassive black hole exists at the center of nearly all large galaxies. In all such galactic nuclei, gas eventually will make its way from the outer galaxy into the vicinity of the black hole. And if the black hole is spinning, then the gas tends to orient in an equatorial plane near the black hole, forming this accretion disk. And you can see this here on the left cartoon. So around the black hole, we have a hot corona of electrons. It's right here. And these electrons, they emit radiation. This goes directly to the observer. However, part of the radiation is reflected off the accretion disk to the observer. And in this process, we also have the fluorescence emission of K alpha lines of different elements. And the most important element, because it's the most abundant element, that's the iron line. So in the plot on the right side, you see the power law from the electrons that hits the accretion disk and the solid line is the emission from the accretion disk, where the very prominent iron line, where the prominent line is this iron feature right here. Now, clearly, the reflected radiation strongly depends on where the radiation has been reflected off the accretion disk. Either it has been reflected far from the black hole, or it has been reflected very close to the black hole. And if so, then general relativity has to be accounted for in that case. So now we also know that if black holes are rotating, then the accretion disk can reach further down to the black hole. And this enhances the relativistic signatures in spectra. So you can see this in the upper panel. Here the black hole is not rotating. Here you have a rotating black hole. And obviously this changes the whole spectrum. While you have for a non-rotating black hole a very narrow iron line, this one here, this is very smeared out for a rotating black hole because it happens close to the emission close to the black hole. So what about this iron line? Let's have a closer look to it. So on the right side, you see a number of panels from top to the bottom. In the first panel, you see the two horns for the iron line. So here you have, I think you can't see my pointer at this point. Okay, so you see two horns. One of them is the disk that is approaching, it's blue shifted. The other one is the receding part of the disk and it's red shifted. So therefore you have two horns. And then you have a relativistic effect, which is the beaming and the transverse Doppler. So one horn will be much more intense than the other one. And in the third panel, you're going to have a gravitational redshift simply because close to the black hole, time dilation takes place. So this means everything is shifted towards lower frequencies simply because time runs much lower there. The result is the lower panel, which shows the line that you will get, the iron line that we will get once the emission takes place very close to the black hole. So now with this method, with these iron lines, people have been performing a lot of research, and this is the plot that summarizes this research. So for sure there are more updated versions of this plot. However, things haven't changed that dramatically over time. On the y-axis, we have the black hole spin. On the x-axis, we have the mass of the black hole. And you immediately notice that there is a huge bias towards maximally spinning black holes. This means more or less all the points are up there at value 1. And there are also, if you look very closely, only upper limits here of spinning black holes. So we don't have that many measurements of spinning black holes. And this means that spin measurements, even though they are very important, they are very difficult to be performed. And now I'm going to show you a very specific example of a spin measurement that has come up very recently. So this takes us back to 2015 when we discovered Markarian 876, which is an AGN, which displayed an extremely gravitationally redshifted iron line. And this iron line was generated by a magnetic reconnection event in the hot corona, so it was transient. So we have observed that only one time. Here we measured only the tip of the iron line, this one here. This measurement was performed with Swift XRT, which is not exactly the most sensitive instrument for such a measurement. However, based on those results, we made very precise predictions for what the NuSTAR mission would actually measure. NuSTAR has a very broad energy band going from 3 keV all the way to 80 keV, more or less. And here you can see the iron line that we simulated and also the Compton hump that we actually anticipated. So turns out that NuSTAR indeed has observed the source very recently for a rather short amount of time, 30 kiloseconds. It's very short. And clearly, if you look at the spectrum, actually these are the residuals. You can see the excesses here compared to the power law, which is the green dashed horizontal line. So these are the residuals. Here at low energies, we have a huge excess, and here we have more or less a break of the power law. So you see two colors for the data points. This is because NuSTAR has two identical telescopes, let's say two telescopes that need to be cross-calibrated once you do the analysis. Now we fit this spectrum with a large excess at low energies and a break in the power law right here. And this is the result. And clearly you see here I added also some data from the SwiftBat to have more statistics. And you clearly see there is this large excess right here. So to establish the significance of this excess, you actually need to perform Monte Carlo simulations, and this is what we have done. So this plot shows the result of 10,000 simulations, the difference in chi-square on the x-axis, and the vertical pink line, this one here, is our reference value from the actual observation. So it turns out that everything that is to the left is good for us, which means it confirms that this is a real measurement. Everything that is to the right tells us that there is some systematics in it. So the measurement is significant to 99.71%. That's approximately 3 sigma. So this is a very broad emission. This means it has to come from the from close to the black hole due to all the effects that we have seen earlier. Now I have fitted the whole thing also with a very narrow line emission, and turns out that for the same Monte Carlo simulation, such a narrow line would be significant only to 50%. So it's very likely it's being emitted close to the black hole. Here I'm going to show you the results of a relativistic reflection model fitting. So this model is rather complicated because it convolves the emitted radiation close to the black hole with its relativistic effects over the entire bandwidth. So it's really complicated. It has a lot of parameters. The result is what an observer, a distant observer, would actually see from the emitted radiation close to the black hole. So what you see on the right here on top, these are the residuals compared to the power law that I showed you before. And you see this also on the nu plot to the left. So this instead is the result of the broad component at low energies and the break of the power law right here. And if we compare this to the residuals, you see they are more or less nicely flattened out. Indeed, the chi-square, the reduced chi-square is very close to 1. And then I applied also the reflection scenario where we convolve the whole model, where we convolve the emission, the emitted radiation with the relativistic effects. And this is the red line, and you can see that the red line more or less follows very nicely the yellow line, which is a very good fit. And again, if we look at the residuals, you also see that the residuals are nicely flattened out, these that are around 6 to 7 keV, where you actually have the iron line. So this is the model component. We infer a upper limit again for the black hole spin, which is an inclination angle for the accretion disk, which is 32 degrees. And this within the arrows, it's consistent with independent measurements performed in the past. I'm not going to walk you through all the parameters here, but one that's very important is also the ionization, the parameter key. This parameter is only an upper limit, and there are other parameters in there. And also for other parameters, we have very huge error bars that we obtain.
1 minute.
Thank you. We simulated with those parameters a black hole spin that is very minimal, the red one, and a maximally spinning black hole. And turns out that if you want to actually tell these two spinning black holes apart, you need 4 times more exposure. So this tells you why these measurements are so difficult to obtain. And the take-home message is the following here. So spin measurements are important because they form jets and they imply the formation of jets, and they accelerate cosmic rays. we are always in the very same situation with very limited statistics. No mission gives you a very long observation time. And Makarian 876 is an explanatory example for such a measurement. And if you want to take a look at this, um, this result has been published yesterday on MNRUS. So I thank you very much for patiently listening, and I take your questions if you have any.